Welcome to the first of a series of workshops slash presentations, information sessions about some of the subject matter that we're thinking might be inspirational to participants in a New River Innovation Challenge, which is a partnership between Waterfront Toronto Conservation Authority, Toronto and Region Conservation Authority, and with the support of the RBC Foundation. I'm Natami Stewart. I'm the Senior Project Manager for Parks at Waterfront Toronto, and I work really closely with all of the people that are going to be presenting today on PLFP, which is my short form for Portland's Flood Protection Project. Before we start, I want you to know that Waterfront Toronto acknowledges that the land upon which we're undertaking our revitalization efforts is part of the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, the Haudenosaunee, and Wendat peoples. And it's now home to diverse First Nations, Inuit, and Métis people. We acknowledge that Toronto is covered by Treaty 13 with the Mississaugas of the Credit. Just for everybody here, just a few notes before we begin. First of all, please forgive me. I have not often made presentations like this without hearing feedback. So forgive me if I'm doing this in the wrong, at the wrong speed, or if you can't hear me or anything, put your hand up or put some messages in the chat. So we are recording and we're going to post this to YouTube. Only the presentations and the presenters will be visible in the recorded version. So I guess that's me, and I guess that means the presentation. If you could keep your camera off during the main presentation, that would be great. But if you if you join a breakout session later, please feel free to turn your camera on then. And we will be having a Q&A at the end, and you can, in order to get your question read, so I'm going to read the questions that are entered into the chat. So put them in by text, and we will read them out, and the presenters will respond. Maybe can you go back a little? I hope that, go back one, please. Just so you know, those are the buttons there, the top right of some people's screens. They might be at the bottom of your screen, but they're usually the top right of your screen. The chat button is important. The camera on off is important, and the mute button is very important. Please, I think you're all muted, but later and for the presenters, please keep yourself on mute when you're not talking. Thanks. Okay, tonight we're going to talk about the New River Innovation Challenge first, and then Meggen Janes and Onur Kutlu are going to make presentations. Meggen was once, not long ago, the Director of Soil and Groundwater Management at Waterfront Toronto, and Onur is a project engineer at Geosyntec who works on the project and on the geotechnical issues relating to building a new river. After we hear from Meggen and Onur, we will be able to have questions and answers, and depending on how many people, we will break out into breakout rooms. And the breakout rooms are really for people to meet each other. So it will sort you out into different rooms where you can, if you're interested, talk to people who might be able to support your team or join a team. So without further ado, the New River Innovation Challenge. We, Waterfront Toronto and its partners are, we're building a river, and the river was designed and set through an environmental assessment process, which is, I guess, a federally, actually, I imagine this was a federal EA, but forgive me, and maybe maybe one of my subject matter experts will correct me, but it's a government mandated process in which we decide, and it's decided how the design of a river will be done and what the impacts of doing this project are. And through this process, we are required to gather data to measure the performance of the river. So we determined how the river would be designed, how it would perform, and now we have to measure the performance of the river. So that process is very much an environmental assessment, like government mandated process. And there's a lot of reporting that happens and a lot of data gathering, but not a lot of it is particularly accessible to the people who will be using the facility. This is an amazing and interesting design and amazing and interesting project, because there will be so much use of this. There will be people all over the place. There will be fish all over the place. There will be all kinds of things happening in this location. And one of the things that we're really interested in knowing is how can we collect and share environmental data from the new ecosystems to incentivize conservation and behavior change in the wider community. So how can we report back not just to the EA regulators, but to the people who are using it about how well this river is supporting new ecosystems, new habitats, and how is it doing in terms of what we thought we were going to see when we built it. So just so you know, you can always go to the website that you see on your screen for updates and relevant dates about the project. So next slide. Yeah. I'd like to introduce Meggen Janes, who is a principal at Geosyntec and a former director of soil and groundwater management and brownfield approvals at Waterfront Toronto. So Meggen, perhaps you would like to say a few more words about yourself and talk about what you would like to see happen in the river. Without further ado, Meggen Janes.
Thanks, Natami, and welcome everybody. It's exciting to be here. Our focus tonight is going to be on earthworks and geotechnical. Some of the work that I've been working on and Onur has been working on, we'll be covering in some snapshot slides here. As Natami had said, I was a former Waterfront Toronto Director of Soil and Groundwater Management and Brownfield Approval, very long title. Now I'm the principal at Geosyntec. My specialties are on environmental management. So as we talk about earthworks, a component of earthworks is environmental strategy and looking at the environmental quality. I look at the environmental management during and after construction so that the river, the parks and roads, so all those features that are constructed as part of the project will have the features, the below ground features, so things that won't be seen in the finished parks and roads and river, that those features will be in place so that it is safe for people and natures. And that's my focus, and it had been my focus as the Director of Soil and Groundwater. I had started working on the project in 2016 and then joined Waterfront Toronto in 2017. I had overseen the pilot test. There was a series of pilot tests, and prior to that, laboratory studies to demonstrate that the soil could be treated and that soil could be reused on site. And we'll talk more about that a little bit later. What does that mean, the soil treatment, and what does it mean to reuse soil? As part of that soil treatment process, it was key to understand what treatment the goals were. So we knew how to treat the material and then how we could reuse it. Also, as part of the role was securing environmental approvals. Natami had mentioned the environmental assessment that was gained in, I think it was 2017, maybe 2016. And there's additional there's some, thank you for the note there, provincial and federal environmental assessment. The additional environmental approvals are needed for developing the land to more sensitive land use. So there's very large environmental approvals in addition to the original environmental assessment. I also worked on incorporating those engineering barriers into the design so that people and nature are protected in the future conditions. And part of the role was developing procedures to minimize environmental effects during construction and also in the long term. So you can imagine it's such a large area and a lot of activity is happening down in the Portlands area. There's a potential to have environmental effects, and there's many, many environmental protection plans that actually cover and work to mitigate any of our environmental effects during construction. Next slide. Thanks. The Portlands area was created about 100 years ago through a lake filling process. As I'm part of the original, some of the very original flood protection works within the Toronto when the Keating Channel was developed to reroute the Don River. An interesting process in itself, just the development of the Portlands area. After the lake filling and the filling of the lands, then the land was developed for industrial purposes. It had many industries that were on site, and you can see in this picture at the very back the bulk oil and refinery that operated. And that is, if you can imagine the New River orientation, the New River actually extends through those lands and then emerges out into Lake Ontario off to the right of the picture. And we're looking south right now on Old Cherry Street. That lovely heritage building there is actually still in place. It's developed around that. That environmental industry, and that industry has left an environmental impacts on the land. I have some fun pictures here during some of the pilot test stages when we were able to recover some of the oil from the ground and look at ways to treat it. So this is some of the example of the oil that's in the ground that is present because of that former industrial practices. That's the significant environmental challenge of constructing a river through these lands that are heavily contaminated with this material. Next slide. When we have such contamination in the ground, we are excavating through it and managing the soils, creating parklands and roads in adjacent areas. When we establish effective environmental management systems, which we'll talk about in a bit, we avoid things like this. And this has always been my worst nightmare, having a fence around a finished park that for some reason can't open because the environmental management or environmental approvals aren't in place. And then on the right, a image of a sheen in surface water. So again, where there's contamination that hasn't been properly controlled and then emerges into the river. So these are the things that we work so hard through, over 6 years of looking at environmental strategy, doing over 300 different boreholes, another 300 monitoring wells to investigate and understand the soil and groundwater conditions through the Portlands area and come up with our really unique and very strategic environmental management system for building a new river. Next slide. The environmental management system are environmental controls that allow us to revitalize this land. And this picture here is looking towards the west. And if you know the site, there is the Heritage Atlas crane. Thank you, Michaela. And if you look in the bottom right, you'll also see that same, there you go, same Heritage Atlas crane. So you can see in the bottom right, the vision for the future of the new river and naturalized areas and parklands on either side and a new road and a new bridge. The image is showing the environmental controls that are placed in the river. Now, through the construction of the river, if you can recall the earlier photo that had that bulk oil refinery industry that was right in this land, much of the soil that was heavily contaminated has been excavated through the construction of the river. So that is fantastic news, enabling us to look at the soil, treat it, manage it, and then reuse it. This is a flood protection project. Not only is it constructing a new river to give a new outlet for the Don River, but it's also raising the grades surrounding the river, raising the grades and lifting it out of the flood, this land out of the floodplain. And to raise the grades, we also need soil. So we have soil that's excavated in the river valley and then managed, assessed, and then placed in locations where it can be reused to lift the elevations and bring that topography up. Within the river valley itself, we have a system of features for environmental controls. You can see on the right side of and the left side of the drawing, the essentially a concrete wall that is the north and south walls of the river. And that concrete wall goes down to 20 to 40 meters into the ground to make sure that that water, the river inside, is protected from anything that may be outside of the river. We also have a system within the river to protect from anything that might be coming from underneath the river. So what you're seeing is that black layer is actually part of the barrier system within the river that's comprised of a geosynthetic clay liner, a geomembrane, and then a reactive treatment layer as a whole multiple layers of contingency to make sure that this river valley is protected. Next slide. Excavating the 1 kilometer length of river is generating about 1.4 million cubic meters of soil. The river valley here, again, we're in the central river valley facing west towards downtown, is about 100 meters wide. In this picture, this was taken probably about, trying to think, maybe 3/4 year ago. So again, the picture on the previous slide was just recent, at near the completion stage of the environmental management system in the river. So the concrete walls on either side of the river took about a year to install all along the edges. So you can see 100 meters wide from the concrete wall to the other side of the concrete wall. And that whole excavation is generating a lot of soil. We have to look at the soil qualities very closely. We look at the horticultural properties, we look at the geotechnical properties and the environmental properties. And when all those properties meet the requirements, then we can reuse the soil in the parklands and roads and the other areas where flood protection, landforms, other areas where we're raising the grades for flood protection. And you can see in the bottom right picture then an example where we are creating the wetland on the south part of the river and reusing some of the soil as the center island within that. Next slide. I mentioned earlier that part of the former director's responsibility was to make sure those environmental protection plans were in place, make sure the frameworks were well thought out, that could ensure that during construction, we really mitigate and manage and control our environmental effects. There is extensive monitoring that's done during construction, and I thought that might be of interest to this group. These are not the only aspects that are monitored, but this is a good data set to consider and amongst all the other data that's collected in the area. Surface water is sampled daily, and it has been daily since I think 2018 and will continue on until 2023. So 5 years of data of upstream and then downstream within the Portland's vicinity. Air quality is also monitored. There's 3 locations where we have continuous monitoring, and then there's additional locations within the construction zone and additional locations that move based on where the construction is at during that phase. Daily and monthly data is collected for air quality. So at the end of the project, there will be a considerable data set, really looking at the surface water quality, beginning at pre-construction, so baseline, and then all through construction. Next slide. One of the questions that was asked of me is, what would I like to know about the Portland's Flood Protection Project in 25 years to assess how it's performing? Now, I know my main interest is on those environmental management and environmental features that are installed, but I'm also curious about many other things. Surface water quality improvements, looking through the data set on surface water pre-construction and some of the sediment quality pre-construction, it's obvious that there's been considerable improvements even before our project. I'd like to see how that continues, how we continue to improve the surface water quality with the Don River renaturalization. Plastic. We see that within some sections of some of the habitat areas that we've already constructed, that plastic is collecting in these areas. And there's some other groups at University of Toronto that have been looking at different ways to remove plastic, and they've been monitoring some of the plastic that comes down the Don River. I'm interested to see if some of those aspects can evolve and we have less plastic coming down the Don River. Lower turbidity, much of that construction surface water monitoring is focused on turbidity. It'd be really nice to see how that's performing over time. And of course, healthy ecosystem in the sediment. My son's class years ago through Toronto District School Board went to High Park, and they did this really fascinating science experiment looking at the benthic organisms that were in sediment in High Park in the pond area at the south end. And it was so incredible to me to see the vast diversity that you could get just from some small samples of sediment there. And it would be wonderful to mimic some of those experiments in the future, and hopefully someone like Toronto District School Board could do something in the New River wetland areas as well. Air quality improvements. Does the ecosystem ribbon along the Don River improve our air? Through the several years of monitoring that we've had the air on site, it's obvious that the downtown area near the highway has some air quality concerns. Do we see any improvements by doing this renaturalization? I think that would be an interesting thing to look at. Mammals and birds, what's happening? One of our project directors at Waterfront Toronto swears that he's seen a fox in the drone footage of the Portland's flood protection site. So we already know that there's some mammals that are attracted to the area. What's going to happen in the future? What are the new mammals and birds that are coming in? And specifically for me, are there turtles? And then finally, probably the closest to my area of expertise is the engineered environmental features. Are they working as designed? Is the river flowing as expected? And how does that river perform in flood events? There's been years and years of hydraulic modeling on the river valley to understand the 2-year, 5-year, 10-year regulatory event floods, to see how the river performs and how all of the structures of the river perform. Does it match with the predictions? Do the naturalized engineered slopes perform well? And are those environmental subsurface controls working well? And thank you very much. That concludes the piece on earthworks. And now we'll be turning over to Onur to look and give us a view on the geotechnical aspects of the project.
I'm just going to interrupt for just a second, and it's Natami again, and remind everybody to put your questions in the chat, please. And can you flip to the next slide? Oh, we will, sorry, questions in your chat, please. We're going to take questions, I think, from both Meggen and Onur at the end and answer them at the end. So don't hold back, please. We'll ask them all. And next slide.
Hello, everyone.
I think Onur's going to bring up.
Yeah, we missed you. We don't have a picture slide of you. So Onur is
Hi.
a project geotechnical engineer with PLFP, but he works for Geosyntec, and I'm so thrilled to have Onur on the project. He really clarifies some very, very complicated things. There you are. Thank you. I actually have never seen Onur's face. I've only seen the graphs that he produces, which are very clear as well. So welcome to Onur, and please do put your questions in the chat. Thanks, guys.
Thank you, Tami and Meggen, for that excellent presentation. Hi, everyone. So my name is Onur Kutlu. I'm a project engineer at Geosyntec, and I mostly specialize in geotechnical engineering. Just to give everybody a bit of a, I guess, perhaps an introduction, as the geotechnical engineering may not be too much of a common field of engineering. So the quick, very short description is geotechnical engineering is a branch of civil / geological engineering concerned with the behavior of the Earth's materials. And it uses the principles and methods of the soil mechanics to solve engineering problems. And as an example, just to show everyone some pictures, what we often say in our industry, in our field, is that what we design or what we work with is just never makes it out of the ground. It just remains in the ground. So I want to take this opportunity to show you as how it looks actually for us and what we do when you go into this building, for example, and how it's actually standing there. And that's pretty much in overall the role of a geotechnical engineer, that we would investigate the ground and come up with a design so that the loads that whatever the design is, this in the picture on the left has this building, the picture on the right has this road, for example. So we look at the data and come up with a solution so that this building can be constructed, or this road can be constructed. So what do I do, and what is my role in Waterfront Toronto project? I mostly work on the geotechnical aspect of the park features. And one of the first things that we do to engineer it is to collect data. Same as the environmental aspect, we need data first to be able to design anything. And I just wanted to show you a few pictures here as to one of the methods that we use commonly to collect data. And the picture on the right that you see is actually a truck that is elevated from the ground a little bit for leveling out. And then it has what's called a cone penetration test, CPT. And the CPT cone actually is after the truck is elevated, there's an operator within the truck over here inside, and then starts operating the cone and starts pushing this cone at a steady rate into the ground. And as a kind of a zoomed out or zoomed in view of how that cone looks like, that you see on here on the left, it has a pointy conical shape, and then it has a sleeve on the back, and then anything that's just beyond that point is just rods that are being added from the inside of the truck as we continue to push this cone. And while this cone is being pushed at a steady rate into the ground, we collect data, and mostly in terms of how much this cone is resisting or how much resistance this cone is feeling as we try to push it in the ground. So the first step for us to collect the data and understand and investigate the subsurface conditions and the materials at the site. So the next thing that we do is to understand, once we have the data, we need to evaluate it. And there's two components mostly that we look at to understand the soil properties. And there's two, there are physical and the mechanical properties. On the left figure that you see a cross-section of how a soil profile it looks like. Mostly, as you'll see in the park when it opens, there's going to be horticultural layers, as you see it's in this picture showed as a grass, and then there's some topsoil, and then there's some bearing layers that has a coarser particles, and then below that coarser particles, in this case, there's a native material that has a brownish color that we likely gonna they call it a subgrade to support all of the design work that's gonna go on top of it. And in the parks, as a depiction, it's not the actual design. It's a depiction that you see again as a organic layers. It's called the horticultural layers for the grass roots and whatnot. It's topsoil underneath it, and then a subsoil, which is generally the bearing layers for the design work lies on top of it. So after we collect the data, interpret the properties, the next thing that we do to understand what are the geotechnical challenges that we have at the site. There are a number of challenges that we look at, but I'll take this time and this presentation to talk about one of them. And this is actually one of the most challenging geotechnical problems that we work with on a daily basis, actually, in the project, and that is the settlement. So the settlement, what it is called is actually it's a mechanical process that soil that goes through over time, and it changes volume in response to the change in the pressures. And as I'm sure everybody or most of everyone here has seen some version of this picture, the Pisa Tower in Pisa, Italy, where the tower is actually leaning and not straight. And the reason behind that is because over time, as this Pisa Tower, after it's been built, and there has been a change in the pressure on the soil supporting it, and over time there has been a differential settlement on only one side of the Pisa Tower, and that's why it's leaning like this. But it has been stable for decades now. But after there's still ongoing settlements, I can tell you that. But it has been stable for a while. But this is one of the perhaps one of the world-renowned landmarks to help you visualize what happens when actually settlement occurs over time. In our project, though, what we are building is mostly fill over existing ground. So in this case, the existing ground is actually the black line overlying what's called the material that's defined as peat. And over that peat, we'll be building, as Meggen indicated, we'll be elevating the grade because to protect it against any flood events, which means that we would need to place soil over the ground surface. And when we do place the soil over ground surface, if there are presence of compressible layers, such as peat, what happens is that when this peat feels this change in the pressure on top of it due to this fill placement, it starts to compress. And as it compresses, it can be a large magnitude of compression, depending on how much load that we are placing or how compressible this peat is. And over time, that settlement happens, and then finally it comes to a stable point. Just to give everyone a bit of a settlement concept analogy, what else, how we look at or evaluate the settlement to design the features or evaluate the design features overlying the subsurface is there's two components to it. there's magnitude, and there's time. Both of them are very important for us to understand how the soil is going to behave. And typically, what we use as an analogy how settlement works is through a box of soil, a box that's filled with water, and there's a plate supported by spring that you see here, and with a hole sticking out of from that plate. And when we place a weight on top of the plate, due to the pressure that's being applied by this weight, this plate starts to move down. And over time, it starts to move down, and due to there's a hose, or outlet from that plate, the water comes out of it, and then at some point in time, this reaches in a certain equilibrium point, and there's no longer any more settlement. This weight is being supported by this spring. And I forgot to mention that the spring actually is an analogy for the soil, and this water is the water in between the soil particles in the ground. As I said, there's two components of the settlement concept: the magnitude and time. And in this case, to help you visualize, the stiffer the spring, as I said, it depicts the soil behavior. The stiffer the spring, that would mean when this weight is placed, there's going to be less settlement. When the spring is softer, there's going to be more settlement. And that is mostly related to the magnitude of settlement, because depending on how stiff the soil is or how soft the soil is, the more the weight that you place on top of it is going to determine how much settlement that you're going to get or occur over time. And then the other aspect of it is the time, which is really a function of how small or large of this outlet is. Meaning that if you can imagine that, if this outlet is relatively small in diameter, that will mean this water is going to escape out of this box very, very slowly, and it's going to take very, very long time to escape under this weight. Or in the other end of the spectrum, if it is very, very large, that would mean when this weight is placed, the water is going to escape out of it a lot faster than this smaller outlet case. So the time is plays in that role, meaning when the soil particles have very, very small pores in between them, the settlement takes quite a long time. But if it is the pores are a lot larger, then that would mean the settlement can happen a lot faster. And here in the picture, so once we actually come up with the design and understand how much the magnitude of the settlement and how long that settlement is going to take, we develop an instrumentation program to pretty much monitor our evaluation that was done in the office and see if our predictions are similar or not in the field. And to do that, there is one of the methods that we use is called a settlement plate. And from the name of it, we place the settlement on the ground with a stick-up pipe that's coming out of it. And then over time that we place fill around this pipe. And then once we reach to the height that we want to achieve, which you see in the picture on the right, actually, this is a picture from the field. You see these pipes coming out of those settlement plates sticking out of the ground. There's fill all around it. And then what we do is on a daily or bi-daily or even perhaps longer intervals, we go out and survey the top of these settlement plates to understand, how the settlement is happening in the field over time. And just to give you an idea of what those compressible layers that I have been referring to, especially the peat layer, is the picture on the bottom left that you see. It's a kind of a darker color material with wood pieces or wood remnants in it, which is one of the actually root causes of the large settlement that we expect, because these roots are actually once these soils were at some point, but over time those woods are decomposed and actually becomes like a soil sized particles, and there's still some left within this block of soil that you see, but the decomposition process of that wood materials is makes the soil a lot quite compressible, and that's why we need to estimate and monitor those the settlement or the compression of this peat material. And on the top figure, there's another compressible layer. Just wanted to share a picture of it. In this case, you see a different, perhaps the deposition time, which because you see there's a layer of a thin gray colored material, light gray color material, and then perhaps a peat deposit that's sandwiched between those interbedded with those thin layers of other depositions. But sometimes what we calculate for the project is not meeting a design criteria that is established for the project. So in that case, we try to come up with some alternative solutions. And one of the solutions that we are actually using in the project is it's a lightweight fill. And this lightweight fill is a broad term, but the lightweight fill that we are considering for the project right now is called a geofoam block. And on the picture on the left that you see those blocks in the white color. These blocks, as you can imagine, they're so light. They're so light that there's even just one or two people can just hold them up and place them on the ground. And if you recall from my earlier slides, one of the key aspects of settlement is the change in the pressure. And if we do not use a conventional soil to build these landscapes or the park features, instead of to use these blocks, that would mean the soil underlying it is not going to feel much of a change in the pressure. So this is one of the solutions that we're actually looking into, as to not use a conventional soil so that there's not much of a settlement. Instead, we're considering to use these geofoam blocks that are so light that wouldn't change pressure, or if it does, there would be very minimal change in the pressure and felt by the soil underneath. And then finally, I'm going to answer the same question as Meggen did, what I would like to see from the project and how it's performing within the 25 years. Well, number one, how I would like to know how the long-term settlement is performing in the areas that we are not going to be using that lightweight fill option. And how in the areas that we will be using geofoam, I would like to see how that geofoam is performing over time. But again, as I showed in my first slide, those geofoams, we will not be seeing them because they will be buried underneath, as in these pathways or the lawns and whatnot. Will be buried under the landscape, but it will be there. As you see on the picture cross section on the right, you see a blocks of geofoam stacked on top of each other with a soil layer on top of it. And this green layer is it could be the lawn yard or it could be the pathways. But it will be supporting, the geofoams will be supporting different park design features as you visit the park. So with that, that is the end of my presentation.
Thanks, Onur. That's so great. Okay, I think our friends in the background working furiously have turned off the presentation and have turned on the camera. So I'm going to read some of the questions that were in the chat, and I'll direct them to Meggen or Onur. The first question that we read or that we had was what water quality parameters were measured, and I'm going to ask Meggen to answer that because we've talked a lot about surface water quality measuring, and I think she probably knows more about groundwater quality measurements. So.
Tammy, is the question on surface water or is the question on groundwater?
It
or
just
both?
says water quality. So
Okay, I'll speak to both then.
Okay.
Groundwater first.
Surface
Someone
water,
said
says,
surface water clarification. Thank you.
But
Thank you.
I think it's actually an interesting question about whether you measure different things and what are those different things that you measure in both.
Yes, because you would in groundwater, you're not looking at aquatic species and habitat. So in groundwater, we're not measuring all the same parameters that we would in surface water. So surface water, they would be doing very traditional measurements that would look at turbidity and dissolved oxygen. In addition, because of our project, then they would also be looking at some of the contaminants. So they would be looking at petroleum-based contaminants and metals as well. So those are the basic types of contaminants. That monitoring would be on a less frequent basis. They would look at doing initially it was a whole series of events, wet events they would do sampling, and then dry events. So making sure that when it was raining a lot, they would get some samples during those periods. And then when it wasn't raining a lot, and not a lot of flow in the river, they would get those periods as well. So you get kind of both spectrums of how much water was in the Don River that might influence the concentrations of those parameters. But things like the general chemistry, we would call it, in the river are measured on a daily basis, and that data set again is frequent. I think there's a couple of samples per day at those locations that I had on the figure.
And do you remember what depth the surface water quality was monitored at? If in some places the bathymetry is 5 meters, like if the water is 5 meters deep, do we send our sampling all the way down, or do we differentiate between different parts of the water column?
That's a really good question, Tammy, and I don't know the answer to that one. I know that when they're collecting the sample, they're using a long pole and dipping into the water. So I can't imagine they're getting down deep. But I do feel that in the historical record that they have more of that stratigraphy of the surface water conditions at depth. But I think in that more routine sampling that's done every day, it is more that upper 1 meter of surface water that's being looked at. But that's a very good question. I don't know the exact answer on that one.
It's also a question. If there are questions like that are pertinent to a potential proposal that a person might be making to this innovation challenge, that it's absolutely worthwhile sending the question to the email that's associated with the competition. I think it's innovationchallenge@waterfronttoronto.ca, but I know somebody's going to put it in the chat right away. And I also wanted to mention that in terms of surface water quality, that our partner, the TRCA, has a lot of other historical and more general, not PLFP specific water quality information in the Inner Harbor. So there's sort of there's likely benthic invertebrate information about the water that comes out of the Keating Channel down the Don and in the Inner Harbor at different times, but I'm not certain what the regularity is, but you can certainly find out by asking the email.
Yeah, that's very true, Natami, because there is regular annual events that Environment Canada looks at. They have designated locations within the Inner Harbor for sampling sediment.
So there's another question about whether there were any systems or technologies to manage soil movement and tracking of the huge amounts of soil generated. Yes, there are. They are complicated, and I think Meggen can answer some of those questions.
Yes.
Because she's been around setting those systems. So
Yes.
go for it.
Yes, I know I had done a presentation at a excess soil symposium several months back, and I had a very similar question, and I was just trying to count how many systems we have on site now that manage and track soil, because there are many, and they are very site specific. So we have one contractor that has the main responsibility as our soil manager, and they have a very unique system that's really been developed for this site, and it has a lot of GPS tracking. They have GPS enabled equipment. So when the equipment moves through different zones, there's electronic records that are captured to track the movement of the equipment, and then set up geogrids across the site so that the soil is tracked from location to location. So that's just one of the soil management tracking systems that we have on site, but there are several others that are used as well. So I believe there are actually 4 different soil tracking systems. Some are very specific to the location, and some are commercial soil tracking tools that are readily available for the market.
Great.
Sorry, just one layer onto that is that there are requirements under the environmental approvals that we have for the site, for the soil management, that require us to track all the information on a very specific basis, and collect that on a daily basis, document, and then produce reports from that.
Super. Okay. The next question is for Onur, and it's just a brief, almost silly, but I'd be interested in knowing how deep the cone piezometers go, and whether they, like, do they make it all the way to bedrock, and what is, how deep do they go, and do they go deeper at PLFT than they do in other places?
Hello? Can you hear me?
Yeah, we can.
Okay. The cones at the PLFP sites, generally speaking, they go about 50 meters below grade. And we do target. Well, it sounds like it was targeted to be getting close to the bedrock, because what happens is the cone can bend easily, especially if you go to deep depths. So it loses it becomes more flexible than rigid as you push to deeper depths. So that's one of the aspects that how deep that we can push a cone, because, like, for example, as you get close to the bedrock, there's going to be some pieces of rock or gravel on top of the bedrock, and as soon as that cone actually hits one of them, and I'm not joking, it could be even just one piece of it, it can start bending the entire rod of the cone. So it's generally 50 meters, but I'm gonna have to perhaps disappoint you, Nisami, because I have seen quite deep CPTs that are over 100 meters. So they can be very deep, but wow. Yeah, it's but yeah. So hope it answers your question.
It does. I know. Just for everybody to know, one of the really cool maps that we had of this site, Meggen knows what I'm going to say, is a map of the depths of bedrock. So the bedrock in this site is cringeworthy. It is very deep, and it's which means that trying to settle things on top, there's a lot of stuff between the bedrock and the top of the ground to squish before you get to a solid construction. And the deeper the bedrock, the more expensive it is to get to it. So it is very interesting. We have a sort of a plan of where the bedrock is underneath, and it's really, really interesting. And this sort of, I'm going to skip over one question, which I will answer in a second.
Nathan, let me add one more thing. Sorry, it's there.
Yeah,
It's actually, I just remembered, it does go quite actually about 40 meters below. I was thinking about some other side part of the project. 40 to 50 meters is a more reasonable deepest range for the project. But yeah, you're right. It's and especially for the bedrock, I don't think this is one of the unique sites that I've seen how the top of bedrock changes this much over a short distance of time. Distances also, it just dramatically changes. Like I've seen some locations also maybe deep 20 or 50 meters just over a short distance. That was yeah. I'm actually happy to hear that you brought that up also. So yeah.
It's very fascinating to me. It's like a perfect storm of all these confluence of environmental and geotechnical challenges. There's a ancient bedrock valley that runs right through the site, which is why we have bedrock at 40 meters depth versus some very steep valley, 20 meters depth. And it's, of course, right through the site. So not only the environmental challenges and the geotech depth of bedrock and the organic soils that Onur mentioned all together, all in one. Very interesting.
So just as a short follow-up to that, Onur, how thick and old is the peat layer? I know that once somebody when they were drilling to find the bedrock, they pulled up some of that peat and they tried to germinate some of the seeds that were in it, and it didn't work. I still hold out hope that maybe we might find some viable seeds, but it's a very remote hope. So I wonder how old that peat is and how old the seeds are.
Unfortunately, I don't have. No, unfortunately, I don't know how old the peat is, but it takes. I know. I can probably say that it takes quite a bit of time to decompose and get to that deposition, I would say. And the thick parts I have seen about 5 meters thick of a peat deposit. So they can be relatively quite thick, which is one of the main reasons why we see quite a bit of settlement also.
I'm gonna guess on the age, and only because there used to be a very large wetland at the location of the Portlands before all that filling happened 100 years ago. And that large wetland would have formed after the glacial Lake Iroquois left or I guess shrunk into Lake Ontario, and that was around 12,000 years ago. So not super old, but still very vast from that old large wetland.
Thank you, Meggen. I learned something new too.
Okay. So just to address a question that I'm not going to answer, which is about whether have you considered crowdsourcing and citizen science experiential learning opportunities within an asset management framework? That's the kind of question we were hoping that the responses to this new innovation challenge could answer. So that's the kind of proposal that's the kind of thing that we're looking for proposals about. I mean, among all of the other various things. So I'm not going to say we haven't considered it or that we have, but it is certainly a really interesting example. So please follow through. Thanks. The next question is about the areas of the New River and whether they're going to continue to settle past 2024 and how much will that change the landscape.
That is a good question.
I'm going to ask Onur.
That is a good question. It will continue to settle. The first answer is yes, it will continue to settle, but we are developing some geotechnical designs so that the impact or that continuation of the settlement is so small that it does not has minimal influence on the landscape or is within the design criteria that we're following. but it
Right,
will
and
continue
I
to
think
settle. Mhm.
I think what is our settlement criteria for the upland in the parkland that's not within the river valley
Mhm.
is, I think, 75
Correct.
millimeters over 50 years. That is what we're going for,
That is correct.
right?
So I will be very interested in
Okay.
seeing the settlement in 25 years.
Yeah, we're all very interested to find out whether the stairs and the lawn adjacent to it are going to be in the same place. Years. So the next question is, how long can geofoam last?
Geofoams can. Oh, sorry.
No, go ahead.
Oh, geofoams can last quite a long time as long as they're protected. One of the challenges with the geofoam is actually, as I'm sure Meggen can speak better than I can on this. The geofoams are very weak against some of the chemicals like hydrocarbons. And as long as they are protected well against those hydrocarbons, they can last quite a long time. So we are expecting that to be, the long-term performance can be quite good for the geofoam.
Thanks. And can the geofoam be tunneled through for an alternative walking exploratory path? Onur, why don't you talk about tunneling through geofoam? I'm going to assume that that's in 50 years as well. Like if you wanted to use it as soil in the future, would that be possible? Like excavate and shape it in the same way that one might if it were just plain soil.
That is a very interesting question, and I have never thought of it if it is, and haven't seen it also. But I'm gonna say it's probably possible, yes, as long as it's, it's as long as we stack up a bunch of those geofoams and then come up with some kind of a support system around it and drill through it. And it can be actually, it would be a very interesting experience for everyone to see it also, I would say, like an underground tunnel with that you see how that geofoam looks like with the, possible.
Yeah, so I don't know whether the question is relating to building something to allow you to see the geofoam that we're building, or whether it's about manipulating it in the future, but we're hoping no, I don't know the answer to I don't know whether the question was about those things, but I do know that the design of the geofoam and the configuration of the geofoam as we're doing now is very carefully designed by not just geotechnical engineers, but by the landscape architects who are the lead consultants on this project, on the most parts of the project, not the bridges or the roads, but for the most part, the land development. And so we're hoping that nobody does manipulate it until it's required in the future. So we're hoping that that's a long-term thing, but it's actually a very interesting question, is what happens to geofoam afterwards. And I think the last question that we have right now is about flood levels. So the question is, maybe this isn't the right place to ask, but sure it is. Everybody on this project knows that the high lake level is 76.02 because it changed halfway through designing the project, and we have had to adjust and figure out whether the design that we have is going to allow to protect the area that we're trying to protect from floods, despite potentially higher lake levels. And so the floodplain, the flood level, the lake level in a high lake level situation is 76.02, and that is, I think the river goes higher than that, but not until farther up upstream. So for the most part, it's I think it's 76.02. For the most part, it's determined by the lake level. More like let artists pretend they're ants. Well, it would be interesting to know what the effect of artist ants would be on settlement in geofoam. It's really interesting stuff. So that was, I think the geofoam is a very interesting answer to a question about how do you build something really fast. So thank you everybody for your interest and for especially being interested in one of the things that sometimes is difficult to find to understand, at least for me, but that is one of the most challenging and most interesting parts of this project. And I'd like to thank Onur and Meggen for talking about their work and for helping to inspire us to think about data produced by this project. So looking forward to your submissions. I really hope that we hear from you in the Innovation Challenge. Thanks everybody. Signing off. Good night.